first question is number 9. Is this the one you asked for?
Yeah.
Okay. So find the surface area of the part of the hyperbolic paraboloid. What's the other name we have for this surface? Saddle. Very good. That lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. Okay, so here's the thing you have to remember. When you're finding surface area, right, what's the formula for it? So you could write surface area, or you could write area of the surface equals double integral over d of
Square root.
Square root.
ds. Yes, and then how is ds defined?
Square root of fx fy plus 1.
Fx squared, right?
Fx squared fy squared plus 1. Oh, d.
Yeah, okay. So ds is determined by the surface whose area you're finding, okay? And then d is the region you're integrating over. So what does that mean? Because there's so many equations going on, it's easy to get it all jumbled up in your head. I'm finding the surface area of the saddle. So that's what I'm going to use to find ds. That's whose partials I'm going to take. Then these two cylinders are going to help me define my region D and figure out what are the limits. And maybe we'll go polar, maybe not. We'll see. So I left it dA. We don't know right now. Does that make sense?
Mm-hmm.
Okay, because there's always going to be like quite a few equations going on. And I think the most confusing thing with this section is who do I take partials with respect to, and then who do I use for my bounds, right? So whoever you're finding surface area of, that's who you're going to use to find ds, okay? All right, so here we go. Everything's already set up. Let's calculate ds, and then we'll worry about the integration region in just a minute, okay? So this z is the same as f of xy, which is y squared minus x squared. So partial with respect to x?
Negative 2x.
Good. And then partial with respect to y? Good. So then we're going to have ds equals square root 4x squared plus 4y squared plus 1 dA. Yes? Put that on the back burner. Now, I'm going to draw the integration region in the xy plane. We have these two cylinders, but we're just finding the surface area of the saddle where it lives over the intersection of those two cylinders. If you look down in the xy plane. So what do they look like?
Circles.
Circles, centered where?
Origin.
Origin, radii
1 and 4.
1 and 2. Very good, you guys. 1. And then that one I'll make a little bigger. Hopefully stacked nicely. 2. So this is my integration region, yes? Okay, it's a little deformed. It's up to you what coordinate system to use. I'm feeling a lot of vibes like we should go polar. Are you getting that feeling as well? Okay, so let's define our region. What would the limits be in terms of theta and r if we were going to go polar?
Theta from 0 to 2 pi.
0 to 2 pi and r?
1 to 2.
1 to 2. Beautiful. Now let's redefine ds so that we're in polar coordinates. So 4x squared plus 4y squared, what would that be?
4r squared.
4r squared. Very good. And what is dA in polar?
R d theta.
r d theta. Beautiful. How are we doing? So good? Okay, so area of the surface is going to be integral 0 to 2 pi. Next one is 1 to 2 square root 4r squared plus 1 r dr d theta. Nice, huh? Very manageable. Okay. First thing you should do, put a 2 pi on the outside, right? Perfect. So 2 pi on the outside. Then we just have integral 1 to 2 square root. Let me write it like this to help you. 4r squared plus 1 to the 1/2 times r dr. Okay? Now we're going to u sub in our heads. Are you ready? Do you want me to write the first line out on the side? Or you can do the whole thing? You want? Okay. So if we let u be
4r squared plus 1.
du would be dr. I have r dr. I don't have the 8. So when I take the antiderivative, what am I going to pick up? 1/8. Then the quantity 4r squared plus 1 will be raised 1 power higher to the, and then what do I need out front?
2/3.
2/3. And then you're going to evaluate all of this from? Good. 1 to 2. Perfect. Then you don't have to switch the limits. Did I ever rewrite the integral or integrand in terms of u? No. We good? See how relaxing that was? Yes, Vincent.
So I did mine like algebraically. I didn't really draw the graph. Is that required that we need this graph?
Yes, because I will put it on the test. You must include a 2D graph of the integration region. Pi over 6. Yeah, are we okay so far? And then 4 times 4 plus 1 to the 3 halves minus 4 plus 1 to the 3 halves. Good? And then that's pi over 6. This is 17 to the 3 halves minus 5 to the 3 halves. Now, I know the back of the book writes it as pi over 6 times 17 rad 17 minus 5 rad 5. But then nothing else cancels. Like sometimes when you do this, then the constant outside can simplify. So I can see why there's a benefit. In this case, I feel like there's no benefit, unless you just don't want to leave it with rational exponents for some reason. But it doesn't bother me one way or another. So if this was like some other number, whatever, 16, or something cutesy that could reduce with the constant, then I would say, yeah, take this step. But it feels pointless. So I don't care where you stop. Good? Okay, so Vincent, put a star in your notes. You would need a 2D graph for this guy. For all of these, you should have a 2D graph of the integration base region. On the exam, I explicitly state every single problem. 2D graph, 2D and 3D, 2D only. What else do I say? No graph. I put that on one of them. Don't evaluate, set up only. So that way, yeah, because a few of them are like that too, so that you don't take forever integrating. Okay?
But
Good?
I still get credit on the homework.
What?
But I still get credit on
Of course, don't worry, I know. Okay, 13. Okay, this one's spicy, here we go. So the part of the sphere, x squared plus y squared plus z squared, I feel like I made this extra credit last semester. So part of the sphere that lies within the cylinder x squared plus y squared equals ax and above the xy plane. Okay, so again, double integral over d ds. Who am I using to find ds?
The left one.
Yes. Now, in order to find ds, I have to have z as a function of x and y right now. Later, we're going to do it over different planes, not just the xy plane. Okay, next chapter. But since they said we are above the xy plane, then I can solve for z as a function of x and y. So z squared equals a squared minus x squared minus y squared. That means z is plus or minus square root a squared minus x squared minus y squared. Which radical should we choose?
Positive,
Very good. Why?
because it's in the positive z axis.
Very good. Perfect. Okay, let's find ds, and then we'll worry about finding the integration region, which is going to be determined by that cylinder. Okay, which is going to make what kind of a shape if you just look at the xy plane?
Circle.
Circle. Perfect. Okay, so partial with respect to x. You need the shortcut, right, that I taught you for derivatives with square roots that have chain rule. You put 2 and the OG radical expression in the denominator, and then what goes upstairs? Yeah, so negative 2x, right? Derivative with respect to x of what's underneath the radical sign. So then this cancels out. Okay, perfect. And then partial with respect to y is going to be almost exactly the same. What's different? Yes. Technically negative y, but in a hot second, what are we going to do to these? Square both of them, right? Okay, perfect. So then partial with respect to x squared plus partial with respect to y squared plus 1. Let me just call this ds now. is going to be square root x squared over a squared minus x squared minus y squared, right? Plus y squared over the same denominator, plus, isn't 1 a squared minus x squared minus y squared over the same denominator? dA. Good? Okay, and then what does this clean up to?
A squared over A squared minus X squared minus Y squared.
So square root a squared over square root a squared minus x squared minus y squared dA, right? And then technically that gives us absolute value of a, but then a is just going to be the radius of the sphere. So we can just use the positive. So we have a over square root a squared minus x squared minus y squared dA. I'm going to leave it right now. I have a feeling we're going to go polar, but let's just leave it till we've committed. Okay, questions on this part? We're good? Okay, now this is a circle. It's a cylinder in 3 space, but in the xy plane, it's a cylinder. Can you identify where the center and radius are right now by looking at it? No? Okay. So then let me copy it down. I'll show you guys a quick little trick. You know this circle. It's just because it's written in rectangular, you're not recognizing it. What?
Is it a cosine?
Yeah, totally. So switch this to polar, guys. The left-hand side would be what? R squared equals a times, very good, r cosine theta. You can cancel the r on both sides when we're in polar, right? You're not losing anything by losing that r is 0 when you draw the graph, so it's okay. So we have r equals a cosine theta. Oh, you know this circle. Who is it? Where's its center?
At A.
No, not quite. Almost. Where?
A0.
Half of it, right? A over 2, comma 0. So that constant a is the diameter. It's always double the radius. And it's centered on the x-axis. The radius is a. So let's draw it. Oh. Okay, this is crucial. So, Vincent, I will put on the test, you must draw a 2D graph. And it's going to be important for this one right here, because notice your limits of integration would come out screwed up maybe if you just imagined in your head. You know what I mean?
Yeah, this one I drew out the circle.
Oh, you did? Oh, bless your heart. Very good. Okay, so here's a over 2. Here's a. Yes? Feeling like we should go polar? Okay, so what would the limits for theta be?
Pi over 2 times.
Yeah, say it the other way. Say negative
Negative
pi over 2 to pi over 2. Very good.
Oh.
Ooh, what about the limits for r? Please be careful. Draw your ray.
0 to
No, it's not 0 to a. Is the radius the exact same amount every single time? 0 to a cosine theta. 0 to the curve. 0 to a cosine theta. Okay. It's 0 to a if it was a circle centered where?
origin.
Origin. Then the distance is always a everywhere you go. You see how this one was shorter, this one was longer, this one was, right? Then it's shorter. Okay, so it can't be to a constant. It's changing. So it has to be a function of theta. The only ones where it's a constant is when it's centered at the origin. Okay, good. Good. Are you ready to set it up then? Let's rewrite ds though, so we're in polar land all together. This is going to be a over rad
A minus R squared.
a squared, yeah? Minus r squared r dr d theta. Good? Okay. So here we go. The area of the surface is going to be integral negative pi over 2 to pi over 2. Integral 0 to a cosine theta. And then a over square root a squared minus r squared times r dr d theta. Are we good? Okay. Can we do the trick where we multiply by the limits for theta on the outside?
No,
No, very good. Why not?
there's a
You have
function.
A cosine.
Yes, we have a function of theta here. Very good, you guys. You can't be tricked. We can make life a little nicer because we're finding surface area of what kind of shape? What kind of surface? Sphere. Is a sphere symmetric over this region? If you imagine, here's the x-axis, y-axis, z is going up, and you're looking at the sphere, would the surface area accumulated from negative pi over 2 to 0 be equal to the surface area accumulated from 0 to pi over 2?
Yes.
Yes. So in that case, I can go ahead, double this, and then go 0 to pi over 2. Do you see? But it all hinges on the surface having to be symmetric over the base integration region. Just because this region has x-axis symmetry doesn't mean you can do it. Remind yourself, what am I finding? I'm finding surface area. So if the surface isn't symmetric over that region, you can't do this. You see what I'm saying? Yeah? Okay. I don't want you doubling stuff willy-nilly and getting things wrong. So AR over square root a squared minus r squared dr d theta. So we're going to integrate with respect to r. Do you need me to finish?
You just use something.
Uh-huh.
And then you plug in a cosine theta, and then you derive with respect to theta.
Yeah. And you use a little Pythagorean identity. You want me to finish it?
Yeah.
Okay. So we're going to use sub in our head. So 2. 0 to pi over 2. I'm integrating with respect to r. This is currently what I would let u be, right? And then du, I'm going to pick up a negative 1/2, right? So a negative 1/2. I'm going to have a squared minus r squared. The new exponent is going to be positive 1/2. So then I'm going to have to multiply by 2. Very good. And that should be everything. And then this gets evaluated from 0 to a cosine theta d theta. Look at us go. It would make a Calc 1 student cry. It would. Too bad for them. Okay, so that cancels, but we do have a negative. Okay, let me just take it outside. Let's see what we're doing with ourselves. Negative 2a, 0 to pi over 2, a squared minus a squared cosine squared theta to the 1/2 minus a squared minus 0 to the 1/2 d theta, right? Yes? Did I lose you? You okay? Okay. Then from here, what would you do? Not yet, not yet. Clean up. Please clean up. So you can take an a squared out, and then you have 1 minus cosine squared theta, and all of this is to the 1/2, right? Minus a d theta. And then this a squared to the 1/2 is also an a. I can factor another a out, and I have negative 2a squared outside now. 0 to pi over 2. Who is this? Sine squared theta. Raised to the 1/2. It's technically absolute value of sine theta, but we're on the interval from 0 to pi over 2. What quadrant is that? 1. So sine's positive there. So then I don't have to worry about putting absolute value. I'll just have sine theta minus 1 d theta. Why 1? Because I factored the a out. Yes? Okay, now it's ugly because this minus, right? Blech. So then you're going to do the old switcheroo and integrate at the same time. Yes, you are. So antiderivative of 1.
Theta.
Good. Antiderivative of negative sine theta.
Negative cosine.
Cosine theta.
Positive cosine theta. And we're going to go 0 to pi over 2. So I switch the order of subtraction here to get rid of the negative. Okay. That looks so nice, right? Okay, and then we're done. So 2a squared pi over 2 plus cosine pi over 2? 0. Minus 0 minus cosine 0? 1. And then for this one, I would distribute the 2 through just because it'll make it cuter. So then I would leave it a squared times.
Pi minus
Very good. Nice. Relaxing? Yes, Roy.
So when you did 1/2, when you did the square rooting of cosine squared theta, you got absolute value sine theta.
I replaced this with sine squared.
Okay.
Yeah, and then it results in absolute value sine theta. So then you look at the limits of integration, because we're in which quadrant? 0 to pi over 2.
1.
Yeah, so sine's positive there.
Do we do the same for A as well? Does it do the same thing?
Oh, A is just the radius of the sphere, so we can assume it to be positive. That's fine. But yes, you should always be conscious that if you have like square root of a variable quantity squared, it's absolute value. Yeah. Yes,
How
Anirudh.
did it go from negative 2a to negative 2a squared?
I took another A out.
Oh, I
Boop.
see.
Yeah.
Okay.
I'm always going to push you to pull the constants outside as you go. Because the less messy the integrand is, your brain can focus better. So just always get in that habit. Push the constants out. Push the constants out. Okay? Good. Yeah, I think that was extra credit last year. Not that it will be this time. I don't know. I spiced that part up. Vincent, just open it once quickly and be done with it. And then lay it on your desk so you stop making wiggling noises the rest of the time.
That's
Okay.
a good bet.
15:6. Number 9. All right. Here we go. Oh, do I need to draw it? No. How about, let me copy it over. Yeah? So let me take a screenshot. Okay, let's cut the video, guys. Can you pick any order? Yes, you can. Well, that's great. Okay, who needed 9? Anirudh? Okay. Press the triple integral over E, f of x, y, z, dv. So you want to do xz as the base. So I'm assuming you're going to have your limits for x be constant. So you want to do dy, dz, dx. Does that sound good? Is that what you did? Okay. Triple integral over E, f, dy, dz, dx. So z is 1 minus x squared. And then limits for x are going to be constant. So x goes from
Negative 1.
-1 to 1. Very good. And then z goes from 0 to 1 minus x squared. Good. Then we look at the 3D graph to get the limits for y. So pretend you shoot a bullet through it. It enters when y equals 0, and it exits when y equals the plane, 2 minus z. Very good. Yeah. Were those your limits?
I had trouble setting it up. So
Okay.
I don't really.
Okay. Do you want me to integrate it, or you're good from here?
Can we integrate it?
Yeah. So let's see. We'll go -1 to 1, 0 to 1 minus x squared, 0 to 2 minus z, and the function that we're integrating is x, dy, dz, dx. So far, so good?
Mm-hmm.
And all the limits make sense. You're okay? Okay.
Wait, question.
Which one? Yeah.
So when we're setting up our limits, we get to choose one of the planes as our base.
Yes.
Y, xz, or zy. We chose xz, and that's why our very outermost limit is the constants, which is going to be one of the parts of the base.
Yes, it has to be.
And then the second part of the base is going to be just like the middle one.
Yeah.
And then the very inside is the one that we use the 3D graph for.
Right. Oh, that's the height of the solid. This is base of the solid. This is height.
Okay.
Okay. And then we have another function. So this is a 4-dimensional quantity.
Right.
Okay. Meaningless. Because it's not like they put a f has no meaning. Yeah. Okay, so we're going to integrate with respect to y. Do you see any y's? No, me neither. So you're gonna have x, and then you're just gonna pick up 2 minus z. And then you have dz dx. Make sense? You can skip the step of writing y evaluated from blah, blah, blah. Okay, now, ooh, this is more exciting. We're gonna integrate with respect to z. What do I do with that cute little x? You ignore it. It's just a constant, okay? So let me just put it like right here. Mind your business, x, okay? And then antiderivative of 2 minus z with respect to z.
Z minus
2
y.
minus z squared over 2.
Good. And this gets evaluated from?
0 to 1 minus x squared.
Good.
Yeah.
Perfect. Then this is going to be negative 1 to 1 x, 2 times 1 minus x squared, minus 1/2 times 1 minus x squared squared. Yeah. Dx? Good. Okay. Negative 1 to 1 x times 2 minus 2x squared minus, let me see, this is going to be 1 minus 2x squared plus x to the 4th. And then it's all times this negative 1/2, right? So minus 1/2 plus an x squared minus a 1/2 x to the 4th. Is that right? I didn't do this one ahead of time, you guys, so let's make sure I don't screw up. Okay, let's combine like terms. 2 minus 1/2 is 3/2, and there's an x out there, minus x squared, and there's another x out there, so minus x cubed, minus 1/2 x to the 5th, right? Dx. It's an odd function, it should be 0. Is it 0? Is that that's the answer? Okay. Good. Yay, symmetry. So odd functions are symmetric with respect to the origin. Think of x cubed, classic odd function. If you integrate x cubed from negative 1 to 1, the amount of area that's below the x-axis equals the amount of area above the x-axis, so it cancels out. That's why I looked at it in 1 second and I knew it was 0. I could tell it was an odd function because it's a polynomial. The power on every single x is odd. There were no extra constants added, so it's odd. It would pass the definition that f of negative x is negative f of x. That's an odd function. Origin symmetry, and the limits being negative 1 to 1 means it's 0. Okay? You could totally do that on the test. I would love you more if you did that. I'd be like, ugh, how slick.
Extra credit.
No extra credit. You just write because it's odd. And then I'd be like, oh my God, this kid's a genius. They remember everything with such precision. Bravo to them. Okay, 17 now. Did I do that one? Yes, I did 17. Okay, who needed 17?
Me.
Mustafa, okay. 17 is triple integral over e 6xy dv. E lies under the plane z equals 1 plus x plus y, and then above the region in the xy plane bounded by the curves y equals rad x, y equals 0, x equals 1. So like in this case, a 2D graph is sufficient because based on how specific they were with the wording, I know what the bounds on z are going to be. You know what I mean? Because they said so clearly it's under this plane, so that's going to be the upper limit on z, and it's above this region. So that's my base region. That's enough for the graph. So just a 2D graph, okay? So let's draw the base region. It's the xy plane. Can you see?
Mm-hmm.
Do you have y equals rad x there?
Yes.
Okay. So y equals rad x, x equals 1. This is the base region for the outside. Okay, so what do you want to do, dz, dy, dx?
I did, yeah, that's what I did.
Okay, so we'll do triple integral over e 6xy dz, dy, dx. So look at the picture. Let's do limits for x. Since they're last, they have to be constant. So x is going to go from?
X from 0 to 1.
Beautiful. What about y?
0 to rad x.
Uh-huh. And then z, look at how they told you e is defined.
So we go from 0 to the plane.
Yeah, 0 to the plane.
So what I did the 3D graph.
You don't
Then-
need it, yeah.
But then when I did it, I projected it over the
Yes,
XY plane.
yes.
It looked weird.
I mean, it's a plane.
Like I had this and I had the triangle.
You don't need the 3D one. Yeah, I know. You have a triangle sitting over this region.
Yeah, but it's like outside. It's like
Yeah,
by itself. So I was like,
no. The plane extends forever. So when you find the intercepts, it should project over this.
oh. I just graphed it wrong. Yeah.
Maybe. Let me see. Because it's x plus y minus z is -1, right? Yeah?
Yes.
So, oh, that looks terrible. You don't need all this, but okay. I love that you went for it, you know.
I didn't know I didn't need it, so
Yeah, you're paranoid now because I scared you.
definitely.
You have this. And then this blue, I mean, it's like here, right?
Mm-hmm.
So the plane extends, it'll live over that blue region. It's just not as obvious because it's not all
Yeah.
happening. The intercepts are not all in the first octant,
Yeah.
so it's ugly. But you don't need the 3D graph. I'll tell you on the test, and the way to know is when they're very specific, under, above, then you know the limits. You know the order. You know what I mean? Do you have a question?
Just a comment.
Yeah.
I think the z-axis or the z-intercept's positive one.
Oh, is it? Oh, did I mess that up? Yes. Okay, no wonder it looked extra deformed. I mean, usually they're deformed, but this was especially okay, whatever. Abort mission. Forget the 3D graph. We'll work on it later. Do you have problems integrating?
No. It was.
Just the 3D graph that you didn't have to do. Okay, so you're in better shape than you thought. Great. Did you have something you wanted to say? Anirudh? No? You're okay? Okay. Moving
Absorb
on.
everything.
You got it?
Yeah, I'm just trying to absorb everything.
Well, it takes time. That it does. Okay, 37. That's next, right?
Mm-hmm.
We need the picture. Let's get the picture. Come here. Who needed this one?
I
You all need it? I put it on the test last year.
see it.
Hee hee. Okay. The figure shows the region of integration for the integral. Rewrite this integral as an equivalent iterated integral in the 5 other orders. What's the easiest one to do first?
DZ, DX.
Just switch the outermost, because then that doesn't change the base region. Does that make sense? Okay, let's draw. Currently, the XY plane is being treated as the, let me spell it out. So go like this. XY plane as the base. That's currently how it's set up. XY plane as base, not plane. As base. Okay. So currently, the limits for x go from 0 to 1 minus y. And the limits for y go from rad x to 1. Ooh, how spicy. Okay. Am I reading it wrong? No, that's right, huh? Oh no, x goes from 0 to 1. I read the wrong one. So x currently goes from 0 to 1, and y goes from rad x to 1. I think you're kicking my podium.
Oh, really?
Yeah, okay. So y goes from rad x to 1. Okay, so here's 1. We just drew rad x a second ago, didn't we? Now this is important. Don't screw it up. What are you shading?
The top part is off the picture.
The top part.
Y goes, yes, very good. Good. Yay. Okay, so now if we're going to switch it the other way around, then the limits for y need to be constant. So y is going to go from 0 to 1. And then x is going to go from 0 to y squared. Very good. So far, so good? Okay, so nothing else changes. So this order, we're going to have 0 to 1, 0 to y squared, leave z alone, 0 to 1 minus y, f dz dx dy. Woohoo, there's 1. 4 to go. Ready? What plane do you want to do next? Okay. I'm going to call it YZ, Kyle, just because it's alphabetical order. But you do you. YZ plane as base. Okay, what is it going to look like? Triangle, right? We have z equals 1 minus y. Can you imagine projecting the solid in the YZ plane? So let's draw the base region. Y, Z, 1, 1. Here we go. And it's this region here, yeah? Okay, so we're going to have to do both orderings, dz, dy, and dy, dz. Let's do with y on the outside first. So y constant limits would go from
0 to 1.
0 to 1. Very good, yeah. And then z would go from
0 to the graph.
0 to, what is the graph?
1 minus y.
1 minus y, very good. 1 minus y. And then what about x? So now you're going to imagine in the x direction, you enter where? X equals 0 at the YZ plane. And you exit where? At this surface, right? Which is x equals y squared. So from 0 to y squared. Good, you got it. Can you see it? You're standing behind, you shoot the bullet that way. We're just shooting bullets through these solids, okay? That's the easiest way to understand it. Okay, now let's switch it around the other way. If z were the constant, the outermost limits, what should they be? 0 to 1 again. And then limits for y. Good. 0 to 1 minus z, right? That one's easy. And same limits for x. Same limits for x. Okay, so then we can write the two orders. 0 to 1, 0 to 1 minus y, 0 to y squared, f dx dz dy. Good? That's one ordering. And then the other ordering, 0 to 1, 0 to 1 minus z. Same for x, 0 to y squared f. And then what are the differentials going to be? What's... Shh, turn that off.
dx, dy, dz.
Dx, dy, dz. Very good. Perfect. Perfect, perfect. Good? Last one. Who needs to be the base now? XZ plane. Okay. So what is this looking like in the XZ plane? It's the intersection of z equals 1 minus y and y equals rad x. So the intersection would be, just think, I need to eliminate which variable if we're in the XZ plane. Y. So substitute in rad x for y into the plane equation and you get z equals 1 minus rad x. That's the projection. Oh, why did it make an arrow? Okay, that's the projection in the XZ plane. That's probably the hardest part. Once you know you're going to have z equals 1 minus rad x, okay, you know what rad x looks like. If you make it negative, it flips upside down. And then this 1 means you shift it up 1 unit. Exactly. Okay. So then let's draw what that's going to look like. Everybody's positive, right? Yeah. Z, x, 1. If x is 1, it's 0. So it's like this. Where do I shade? Look at the solid. Underneath it, right? This. Okay, perfect. So let's do limit for x or constant. X is going to go from
0 to 1.
0 to 1. Z is going to go from
1
Z would go from 0 to 1 minus rad x, right? Just look in the z directions like this. enters at 0, exits at 1 minus rad x. And then limits for y, now we need to go to the 3D graph. Are you ready? I'm going to scroll up. So for y, imagine, shoot a bullet into the solid in the y direction, this way, okay? It enters at this surface, so y equals rad x, and it exits where? Y equals 1 minus z, right? So we're going to go from rad x to 1 minus z. Rad x to 1 minus z. Are we all right? Okay. Then the other ordering would be z is constant, so z would go from 0 to 1. X, ooh. So we have to clean this up a wee bit, yeah? So rad x equals 1 minus z. And then x is 1 minus z squared. So x would go from 0 to 1 minus z squared. And then same limits for y. Same limits for y. So then you would have integral 0 to 1, 0 to 1 minus rad x to 1 minus z. F, what's the ordering for the differentials here? dy dz dx, good. And then the other one, 0 to 1, 0 to 1 minus z squared. Oh, rad x to 1 minus z, f dy.
dx.
Good, you guys got it. You just have to do it again on your own, okay? However many times till you feel like you got it without me by Thursday. Even if you take some unsuspecting neighbor or family member and be like, sit down, I'm going to walk you through this. That's the way to get it under control. Okay? Yes, Kimberly.
I know you'll never ask us to do all this and then integrate.
Right.
But if we did this correct, it should all integrate to the
Of
same thing.
course, because math is beautiful and works. Yes. So if one doesn't match, then you messed up somewhere. Yeah. So the idea is, if you can imagine, then you're ready to like set it up in the most convenient order, hopefully, right? Because if you just have to actually evaluate one, you can look and say which one would be the least painful to do, you know? Okay, good, you guys. That was hard. I think those are the hardest. I was talking to Gupta about it. He's like, ew, I hate those ones. And I'm like, but it's so good to make sure you understand what's
He would
going
definitely put it on the
on.
test, too.
He would definitely put it on the test. Of course he would. Are you kidding me? Okay. Last one, 15-7. The worst is over. I could do cylindrical all day if you let me. You know? Tomorrow I have to bring the book on Jacobi, the other calculus book, because I'm going to read you his bio.
And the cake.
And the cake. What a day we're going to have tomorrow. And I'm bringing the machete so we can cut. I don't really have a machete. I'm just bringing my chef's knife so we can cut the cake. Some of you guys will have the deformed cakes because I'm going to cut it, you know. Is that on the bias? Yeah. So we can really get into it. Okay. 23 and 25, that's it? These are so cute. 15-7. So 25 says find the volume of the solid that's enclosed by the cone. Oh, so nice they're telling you it's a cone. Z equals rad x squared plus y squared. And the sphere, x squared plus y squared plus z squared equals 2. Okay, so we're going to do triple integral over E dv in order to get volume. Does that make sense? Yeah? And since we're going to be in cylindrical, then most likely it'll be r dz dr d theta. Okay? There's a problem on the practice test where it's the other way. You have to do dr dz d theta. It's tricky, so we'll work on that one together for classwork. Okay? I'll do that one with you because you might cry. Okay. So first things first, if we're going to draw a good graph and figure out the base region, did you find where the intersection is for the two surfaces?
Yeah.
Okay. So squaring this, you get z squared equals x squared plus y squared. So then you can replace z squared or x squared plus y. I think let's just replace everything so that it's in terms of x squared plus y squared.
That's good.
Yeah. So then you have x squared plus y squared equals 1, right? So it's going to intersect the integration region is just our good old unit circle, right? Okay. And I would want you to just draw that, show it. Hopefully it's like free points to just do the 2D graph. Say this is 1, 1, boom. So you should know theta and r's limits now, right? Theta's from?
0 to 5.
Good. And r?
0 to 1.
Why is it a constant this time for r?
What's centered at the origin?
Very good. So when the circle's centered at the origin, then the limits for r are constant. Okay, perfect. Now for the limits for z, we should draw the 3D graph. So we have a cone. Are you okay, Oliver?
Yeah.
Did I do something that confused you? Okay. Okay. It's only the top half of the cone, right? Because we only have the positive radical. So it's opening upward. And then the sphere, that looks terrible. The sphere's radius is what? No. What's the sphere's radius?
Right, so
Rad 2, which is approximately
1.4.
1.4. Very good. Okay, so they intersect in the unit circle where x squared plus y squared is 1 and x squared plus y squared is z squared. So it happens when z is 1. The radius of the sphere, though, is like 1.4, rad 2. So I'm going to say this is rad 2. Rad 2. And you can imagine the sphere's coming through like this. But maybe that looks terrible, but it's okay. All right? And I'm not going to draw the rest of the sphere. I'm just going to draw the solid. It's enclosed by the cone and the sphere. Did they say more? No, just enclosed by the cone and the sphere. So it looks like a snow cone. Can you see that? Okay. So now, to figure out the limits for z, I'm going to shoot a bullet into the snow cone this way. The bullet enters where?
Cone.
Whose equation is what in cylindrical? Z equals r. Very good. And the bullet exits
The circle sphere.
at the sphere, which is z equals?
2 right.
Very good. So we'll choose the positive because we're above the xy plane, right? So from r to rad 2 minus r squared. Good? So you see you need the 3D graph to figure out the limits. We'll do other ones where it's scooped out in the reverse situation. So we'll look at some more today, okay? Do you need me to help you integrate from here? Okay, you got the rest. Beautiful. Yay! Fun? Cylindrical is my favorite. Okay, that's it. Very good. Don't forget to like, subscribe, and follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later. Mwah.